Okay, so let's move on to the conservation of momentum and how it assimilates itself into this derivation. So the conservation of momentum. Okay, so we know that what this law states is that the momentum before has to equal the momentum after. So we know that the momentum of the photon before plus the momentum of the electron before must equal the momentum of the photon after plus the momentum of the electron after. And we know that, there we go. Since we know that the electron before, as I've said in the diagram, is at rest, we know that the momentum before is 0, so we can take this out of the equation. And let's solve for the momentum of the electron after. So let's shift things around, and what do we get? We get that the momentum of the electron after is equal to this. Just simple rearrangement. Okay, now the next step involves calculus, but I'm aware that some of you may not know calculus, so I'm going to approach this using vector diagrams. Okay, so we know that since momentum is a vector, we can draw this equation out as a diagram, and let's draw it out as a diagram. So let me just not draw this arrow because it might be confusing. So the momentum vector of the electron after is equal to the momentum vector of the photon before minus the momentum vector of the photon after. So let's draw the momentum of the photon before, and we know that it's like a straight line, right? And let's say this is momentum of photon before, and we know that it hits the electron, and afterwards it bounces off. The photon bounces off at some momentum like that, and this is done at an angle theta. Okay. Now, how would we draw this equation out? Well, we would just subtract this vector from this vector. So let's do that. And we know that in order to subtract, we basically flip this vector over. So in flipping it, we get it like that, and we know that this is it. So the momentum of the photon before minus the momentum of the photon after is equal to the resultant vector of the momentum of the electron after. And we know that since this angle right here is theta from the diagram above, we know that this angle, internal angle here, is theta. Now, in order to find the scalar momentum, the value of this, the length of this side, this vector, we use the cosine law. And the cosine law is this. We just prime squared equals to p gamma squared plus p gamma prime squared minus 2p gamma prime cos theta. This is the cosine law. And we can see that this variable is almost close to the variable right here. So we know that we're almost there. Okay. Oh wait, I just noticed something. Why is this a 4? It should be a 2. Okay. That was weird. Why did I do that? Okay, so in order to make this variable appear in this formula, we basically multiply both sides by c squared. So let's do that. Multiply by c squared. Let's do it. Pe squared c squared equals to p gamma squared c squared plus p gamma prime squared c squared minus 2c squared gamma momentum of the gamma after cos theta. Okay, so what can we get from this? Well, we know that according to the momentum of a photon that I talked about in a previous video, we know that the momentum of a photon equals to hf over c. So knowing this, we can sub in this for the photon. So let's do it. Pe squared c squared equals to, and let's sub it in, so we get h squared f squared over c multiplied, squared, sorry, because I squared the whole thing, squared equals times c squared plus, we do it again for this, we get h squared Oops, I was supposed to use blue. H squared f prime squared over c squared multiplied by c squared minus 2 c squared times hf over c multiplied by hf prime over c, and then we end off with a cos theta. Okay, now we can simplify this further, and we get p e squared c squared equals 2, and we cancel out these two terms. We get h squared f squared plus cancel out these two terms, and we get h squared f prime squared minus cancel out these two terms here, 2 h squared f prime cos theta.